I've been talking as if everybody agrees atoms exist, correct? So if somebody came to you and they said they don't believe atoms exist, could you offer them proof that atoms exist? Sure? Okay. Yeah, and pretty much there's, you can weigh single atoms on a mass spectrometer, you can see these. But think about back in the 1800s, what kind of proof did they have that atoms existed? This is around Dalton's time. The Greeks, I guess, came up originally with the idea of small particles, but Dalton framed it a little differently. He said the smallest piece of matter is the atom, and there are different types of atoms. And so these are the basic points of Dalton's atomic theory. Each element is made up of individual particles called atoms. Atoms are invisible, although now people have visualized single atoms using the glow. Did I show you that? The glow of a single atom?
Yeah.
You remember that? So, yeah, in that case it was visible. Or this is indivisible, sorry. Indivisible means what?
Split out.
You can't split. Actually, you can, but what happens if you try to split an atom? For example, if you try to split a carbon atom into smaller pieces, then you can. You can split it into protons, neutrons, and electrons, but do those protons, neutrons, and electrons behave like carbon-12? No. And so what happens is they lose their chemical properties, or physical properties that identified it as the element carbon. Atoms of one element are different from atoms of any other element. Okay, how are they different? Well, they weigh different amounts, right? Like hydrogen and helium weigh different amounts. But is that the only difference? No, that's not the only difference. And this is what we're going to spend a lot of time talking about, how the atoms differ from one another, which gives it the properties. And in fact, we're very interested in the composition and structure of the atoms. This is just part one of that. Atoms of one element combined with atoms of other elements to form chemical compounds. So compounds are two or more elements. They are mixtures. These are actual chemical combinations. That is, they're going to have fixed ratios, fixed composition. So you don't really have to memorize each of these points. Just have the general feel for Dalton's atomic theory. But Dalton proposed this at a time when there were a lot of skeptics. And this is how the scientific method works, because could he look in the answer book, for the answer? Do atoms exist? Yes, I saw it in the answer key. No, he had to convince people, right? And there are a lot of people who said he was wrong. Because what evidence did he have? And so what evidence did Dalton have? Nowadays, for us, it's very easy to prove the existence of atoms, but in Dalton's times, it wasn't so easy, because Dalton had what? Evidence for the existence of atoms. In other words, did Dalton all of a sudden hypothesize this? I mean, this came out of some kind of, probably a lot of people hypothesize, you keep breaking things down smaller and smaller, how small can you get? And a lot of people said you can get infinitely small. There's no end to how small of a piece of carbon-12 you want. You can just keep making it smaller and smaller. However, Dalton said there is an end. And it could have been some kind of dream, but it wasn't. This came through the scientific method. And what was it that led him to hypothesize the existence of atoms? Well, it was a hypothesis before, but this definitely led him to hypothesize the existence of atoms. Do you know what that was? I don't know if did I talk about this? Maybe not. So let's talk about this. So what led to Dalton's atomic theory? Well, sometimes things come up serendipitously, but this didn't come up serendipitously just by chance. No, this came from observation. And so what observation led to this? What observation led to this is the conservation of mass. this is the law of the conservation of mass. That is the total mass before and the total mass after any change, chemical change or physical change is the same. There's no change in mass. And so you think, well, the conservation of mass, this was the observation, conservation of mass, reactions weigh the same before and after. This is a pattern that repeated over and over. Over and over. It didn't matter the type of reaction, any reaction, the same observation took place. Since the same observation took place, then we ended up with a law. So the law is the law of conservation of mass. And then came the hypothesis. So the hypothesis was that atoms matter must be made up of atoms. That was the hypothesis. And then, with this hypothesis, so you propose this hypothesis. Hypotheses are tentative fundamental explanations. They're tentative because they don't have widespread acceptance. And so they don't have widespread acceptance because a lot of people were thinking that the opposite is quite true. There is no smallest piece. No such thing. You can just keep making it smaller and smaller. And so he had to argue his point. When he argues his point, well, what evidence did he have? What evidence he had was the conservation of mass. Does that seem like very convincing evidence to you for the existence? No. I mean, most people would say, no, that's not enough, right? That's not enough. But based on this hypothesis, he was able to propose a new unforeseen observation. Do you know what the new unforeseen observation that he was able to propose? And this pretty much sealed it, because a theory should do two things. What should a theory do? A theory should be a fundamental description of what's happening with the conservation of mass. What's happening with the conservation of mass is the atoms don't disappear. The atoms just get rearranged. And so whatever atoms you start with, you have to end up with the same atoms. And so that was the fundamental description of the conservation of mass, but theories just can't be a description. Theories have to propose new unforeseen results. And the new unforeseen, so one, it described this conservation of mass. Described conservation of mass at a fundamental level. And two, it has to propose something new, unforeseen, and the proposed predicted, we call it, the law of multiple proportions. Because if mass were infinitely divisible, what's to say you can't add a little bit more hydrogen to your water? Let's say your normal water is H2O, but can I just add just a little bit more hydrogen to the water, like make it H2.10? No, or a little bit less, H1.90? No, that doesn't work. So, so that was pretty convincing, because if matter were truly infinitely divisible, then what's stopping it? And so if matter occurred as individual particles called atoms, then that's what's stopping it, And so that was observed, like H2O, H2O2, etc. And so that pretty much sealed it. But at the time, nobody had seen an atom. And there are plenty of detractors. And so this is pretty significant. And so here's a little pictorial diagram. in mind this is the 1800s, so some things have changed a little bit. So an element is made up of atoms. That's fine, that hasn't changed. All atoms of a given element are identical. Is that true? Are all atoms of hydrogen identical? In one respect they are, because all atoms of hydrogen behave chemically identically. But in another respect that's not true anymore, because some weigh more, some weigh less, and we call those isotopes. So Dalton didn't know about isotopes, and so this is not correct anymore. Atoms cannot be created or destroyed. Is that true still? No, because Dalton didn't know about nuclear chemists, nuclear physicists trying to create new radioactive isotopes. In fact, all these, do you see all these ones that have been pasted in here? MTDS, EG, all those are man-made atoms. They're man-made atoms from other atoms, so they take smaller atoms, fuse them together to make bigger atoms. That's part of nuclear chemistry. But nuclear chemistry is a little bit different. We aren't in nuclear chemistry, we're just in chemistry. And I'm going to talk about nuclear chemistry briefly today, but all atoms of any given element have the same properties, including mass. So these are two, let's say these are two hydrogens. The two hydrogens are going to have the same properties, including mass. Okay. But we know that's not true because of isotopes. They'd have the same properties other than mass. But atoms of different elements, this could be, actually this cannot be helium. Why cannot that be helium? Because helium weighs more. And so this has got to be a lighter, smaller atom. So, you know, this could be, for example, this could be helium, this could be xenon, you know, another gas. Atoms of different elements have different masses. Well, that's true. Atoms of different elements do have different masses. Is the mass the only thing? You know, based on what you know about the mass, you know, we can make some simple predictions. You know, is it more dense, less dense? You know, there's way more, way less. So, for example, helium. You know, helium is very light gas, not much. But something like xenon is very heavy gas. Xenon actually sinks. Argon sinks. Neon and helium rise in air. But some of these other gases will sink. Atoms of different elements may combine in the ratio of small whole numbers to form compounds. This is the law of multiple proportions here. This was a prediction based on Dalton's comment. And you know, the more compounds they observe, the more they recognize that this is the case. This would be like CO2. This would be like CO, carbon monoxide. But you don't find, do you find CO 2.1? No. Those you don't find. And this is a pictorial view of the. So we got one oxygen, two oxygens. What about CO3? You know, we call this one carbon monoxide. We call this one carbon dioxide. How about carbon trioxide? Carbon trioxide. You know what we call 4? Let's say CO4. CO4 would be called carbon 4. You know the prefix that goes? Tetra. Tetra is 4. So that, you know, if I had CO4, that would be called carbon tetraoxide or carbon tetroxide. 5 is pen, so carbon pentoxide, carbon hexoxide, carbon heptoxide, carbon octaoxide. 9, do you know what 9 is? Nona. So carbon nonoxide and finally carbon decoxide. Do we see those? Have you ever seen carbon heptoxide? No, never. Why? So we don't know enough to understand. This is just at the observation stage. And, you know, okay, carbon, you know, tetroxide, I've never heard of it. Does it exist? Maybe it exists, but I just don't know. Or maybe it doesn't exist. What do you think? You know? And so there are different levels. For example, Here, okay, we memorize it. So we memorize there's carbon monoxide, there's carbon dioxide. There's no such thing as carbon trioxide, carbon tetroxide, carbon pentoxide. Those don't exist. How do I know? Well, I could memorize that as factual knowledge. Those don't exist. Right? But do I want to memorize everything? No, it's too much. So I got to start looking for patterns, and this is what I'm going to do. I'm going to start looking for things that clue me in structurally, why this is the case. If I understood the theory, that would help quite a lot. But right now we're just going to look for the patterns, which we'll be looking at soon. So on that exam I gave you, I think one of the questions was carbon trioxide. Was that one of the questions? Did anybody look at the exam? Question on the exam? I forget. What's that?
Was it toward the end of the test? Because I don't remember.
Okay.
I sent it in an email.
Let me see. I thought I saw that and I thought, well, I'll tell you, in the summer, there's less time. So we jumped right to the patterns immediately, looking at patterns of this type of stuff. And so I try to tackle the memorization early in the summer rather than wait. In our class, we could wait a little bit for it. So a question like number 20, a question like number 20 would tell us the answer about carbon. Although we'll probably talk about this anyway, so in chapter 5. This oxidizers, this kind of stuff. This kind of stuff, tells us, why carbon trioxide. We don't see that, or at least it shows us a pattern in which we can predict that carbon trioxide, carbon tetroxide is going to happen. This would be a follow-on. I could have done this, which I've done in the past. Carbon, which is called soot. We looked at soot in the lab, remember? It's mostly amorphous carbon, graphitic carbon. No diamonds in soot, unfortunately. Carbon monoxide, carbon dioxide, and carbon trioxide are all potential products. Yes? But you'd have to know a little more, right? To say no carbon trioxide. No. So that would be a follow-on question in chapter 29, for somebody who understands it with a little bit more depth. So there's some chemical stuff in the test, but since again it was summer, let's talk a little bit about this fall. I didn't jump. I'm not jumping ahead like in the summer. I jumped ahead a whole bunch of stuff, so people could absorb it over a longer period of time. Well, we talked about the electron. The electron is about 2,000 times lighter, or 1,837 times, 1,1837 the mass of the hydrogen nucleus. The hydrogen nucleus, we've got to talk about this, the nucleus. I haven't talked about the nucleus yet. We want to understand more. We've got to understand more than just the weight. It's easy to weigh these things using, what was that thing called? Mass spectrometer. It's easy enough to weigh these things, but the weight isn't going to tell us enough. So we've got to start looking at the structure. Who is the electron? Who's credited? Who was credited for the discovery of the electron? J.J. Thomson. Normally, I don't care about the names, but this is a name that's pretty important. You might see. This happened in the 1800s. Now, as we try to understand the chemistry is more, like carbon monoxide, carbon dioxide, and then it stops there. Because when you completely combust something, have you heard of complete combustion versus incomplete combustion? Complete combustion always results in CO2. If you have incomplete combustion, you could get soot, and you can get carbon monoxide. That's what happens when you have incomplete. That is when you don't have enough oxygen. When you have plenty of oxygen, you can oxidize it completely, what we call oxidation. And so we can oxidize our fuel completely. When it's oxidized completely, it goes to CO2. Well, we need to understand it in a bit more detail. So we want to see how, we know the composition because I told you the composition. I told you the composition, electrons, protons, and neutrons. And we have a special symbol for the composition, which I showed you also. But let's break down, this is called the nuclear symbol. So if I have the element carbon, this is just called the symbol. The nuclear symbol differs from the regular symbol a little bit. The nuclear symbol is usually given by this. So carbon with a superscript 12 in front, and then there's a 6 down below. This 6 is optional. Because what element number is carbon? If you look at the periodic table, those are the red numbers there. Carbon is always element number 6. And so this 6 is redundant because carbon is element number 6. Okay, the nuclear symbol's broken down like this. There's a 1 or 2 letter abbreviation for the element. This is what we call a symbol. So, for example, neon would be NE, capital N, lowercase e. And then we have 2 numbers associated with that. We have one number that's called Z, and another number that's called A. A is equal to the number of protons plus the number of neutrons. Z is equal to the number of protons. And so if you looked at all the hydrogen atoms that I showed you earlier, all of them have the same number of protons. And so it looks like the chemical properties depend on the number of protons. If you look at the carbon, we had carbon 12 and carbon 13. Both carbon 12 and carbon 13 had 6 protons. Both carbon 12 and carbon 13 have the same chemical properties. So the chemical properties must be related to the number of protons, because the number of protons must dictate that. But it actually turns out to be a little bit more complicated than that. And so here. Now, when we think about the mass, the mass of a proton weighs about how much? 1 U. The mass of the neutron weighs about 1 U. Now, A is called the mass number. The mass number is not a mass. So, for example, carbon 12 weighs about 12 U. Well, actually it doesn't. Carbon 12 weighs exactly 12 U. Why does carbon 12 weigh exactly 12 U? Because some guy, I don't know who, I probably should, but some guy decided that we need to change to carbon 12 because before carbon 12 it was oxygen 16. So, well, anyway, and a lot of people agree, and so it was changed from oxygen 16 to carbon 12. Carbon 12 just is defined that way, but every other element is approximate. So carbon 13 weighs approximately 13 U. But when we look at carbon 12, well, that's special, but carbon 13, is this the mass? No. We expect the mass to be approximately 13. And so how many sig figs are in this number here? This one is infinite sig figs. I'll just abbreviate sig figs SFs. This is infinite sig figs because carbon 13 has 6 protons and 7 neutrons. Okay, can you have a part, so is there uncertainty? If it's 6 protons, can we have 5.9 to 6.1 protons? No, it's not possible because if you break it, it's no longer a proton. You can break protons down into smaller particles, did you know that? But they're not going to behave like protons anymore. You're going to have these quarks and whatever else you have. And so for chemists, we stop here. And so these can be further broken down, but we aren't going to worry about that. And so this number is equal to 13. this number is this number here. Now that means it's going to weigh about 13U. So the mass is approximately 13U, but this is an exact number here. And so some people get this confused. As a real mass, it's not a real mass. And so this is what we call the nuclear symbol for this. And so this tells us the composition. We're going to come back to this symbol, but what we need to know is, okay, now I got the composition. I can figure out the composition for carbon 13. Carbon 13 is 6 protons, 7 neutrons, and 6 electrons. That's it. The 6 electrons don't weigh much, so those aren't going to impact the mass very much. But the situation comes about, well, how are these particles arranged inside the atom? We need to know the structure, the structural arrangement of the atoms. Looking at the structural arrangement, now, two hypotheses came about. And in this case, now, okay, we have the atom, now we're just trying to figure out how the atoms are arranged. Well, this is a case where, okay, initially a hypothesis came out and then these hypotheses were tested. And so this is kind of similar to what biology do for the scientific method. One hypothesis is the plum pudding model. In the plum pudding model, the model of the atom proposed before the discovery of the nucleus, the negatively charged electron particles are embedded within positively charged spherical gel. And so it resembles plum pudding, where the plums are the electrons and the pudding is positively charged spherical gel. And so what that means is that it was kind of uniform. The distribution, the electrons were spread out randomly and distributed over the entire atom. And the entire atom had a net positive charge. And then the electrons balanced that charge here. Well, it turns out the plum pudding hypothesis was wrong. Well, we have, and the plum pudding could be tested here, what we have is this experimental observation that pretty much sealed the fate for the opposing model. The opposing model is called the nuclear atom model. The nuclear atom model predicted this. It predicted the atom consists mostly of empty space. In this empty space, the electrons are found. And then there's a tiny nucleus in the center. And so if this were, let's say, if this were a football field in diameter, the nucleus would be like a, what would the nucleus be? Nucleus would be like a golf ball, or even smaller. I think it's like a centimeter. But the nucleus is tiny. Inside the nucleus are all the protons and all the neutrons. And what sealed this was this experiment here. The experiment is called the gold foil experiment because what we have in a piece of gold foil are we have gold atoms. And they can get a very thin piece of gold foil like this, called gold leaf. The gold can be hammered into extremely thin layers like this. This is only 2 atoms thick. And so we have some gold foil here. It could be more than 2 atoms thick. We'd still see the same thing. Now, over here, there's a radioactive atom. Actually, a whole bunch of radioactive atoms. And they're all the same atom. And these radioactive atoms here, when they break apart, radioactive atoms are unstable, they'll break apart into more stable atoms. Not necessarily stable, but more stable. They still could be radioactive. They eject alpha particles. This is the symbol for alpha. We eject alpha particles. Alpha particles, you know what alpha particles are? Alpha particles are chunks of the nucleus. And so a small chunk of the nucleus of an atom, that is the center part, breaks off. That small chunk with the center part that breaks off consists of 2 protons and 2 neutrons. 2 protons and 2 neutrons is called an alpha particle. They're put together. And so these are breaking off continuously. And so we have alpha particles shot here. Now the thing about this is a chunk of the center part. That chunk of the center part is positively charged. And so what happens is most of these alpha particles go straight through the film because the atom's empty space. So most of these alpha particles shoot straight through. Some are going to be deflected at light angles, the ones that come close to this, because this is positive. So if an alpha particle is positive, this is positive, there's going to be a repulsion, positive repulsion. Ohm's law. And some of them will strike it directly. If they strike it directly, then there's going to be significant repulsion, because you can't push positive into positive without resistance. So if you try to push positive into positive, it's going to bounce back and be repelled. And so the ones that strike directly, a direct hit of the nucleus, are going to bounce back. And so they put a detector here, and they see the majority of particles were undeflected. Some were lightly deflected, and a small fraction were highly deflected, telling us gold consists mostly of empty space. Whereas if this were plum pudding would be all deflected at slight angles or go through. There would be no high angle deflections like this. Here. This is another name you should be familiar with. J.J. Thomson was one. J.J. Thomson for the electron. And you should know this name, Rutherford. Rutherford, we usually associate it with gold foil, so we call this the Rutherford gold foil experiment. What did J.J. Thomson do? The electron. What did Rutherford do? Rutherford pretty much, yeah. Rutherford gold foil experiment pretty much confirmed the nuclear atom model. That is, the protons must be concentrated in the nucleus. The electrons are scattered in this empty space. And so Rutherford gold foil, you don't have to know the exact details. It's just he shot alpha particles. And we got these bizarre results. All right, so let's talk briefly about the nuclear atom model. The nuclear model of the atom, every atom contains a small and extremely dense nucleus. The nucleus contains all the atom's positive charge and nearly all of its mass. And so, it's kind of weird to think about, but atoms have a lot of empty space. And electrons, the major volume of atom is nearly empty space. The space outside the nucleus is thinly populated by electrons, so the electrons sparsely populate that. The total charge of electrons balances the positive charge of the nucleus. So the number of protons and the number of electrons are equal, and the way we maintain what we call electrical neutrality. What was the density of gold? About 20 grams per cubic centimeter or milliliter, right? But did you know gold is mostly what? The gold atom is mostly empty space. If you could take just the nuclei of the gold atoms and get rid of the empty space, if we could just take the nucleus, or we just take one nucleus, do you know what the density of a gold nucleus is?
18.
It's got to be higher because we're going to eliminate all the empty space. So we're just taking the nucleus itself. Actually, the gold atom is actually more dense because the atoms don't pack together so nicely. Atoms, there's void spaces and gaps. But if we just take the nucleus here, the nucleus has a density of roughly, and this is a calculation you do in Chem 1A, but the density of the nucleus, I think, was 20 tons per cubic centimeter. And so gold is 20 pounds per cubic centimeter, and you're looking at 20 tons per cubic centimeter. This is a huge difference. So this tells you how dense the nucleus is. The atoms are mostly empty space. Something of that. I got to double check that calculation, but it's something like that. So here it is. The diameter is about 10 to the minus 10 meters. Do you remember what 10 to the minus 10 meters is called? 10 to the minus 10 meters is defined as something. It has a special symbol. We can use different units here. I'm surprised they use this one because 10 to the minus 10 meters is defined as a capital A with a little circle on top, which is called an angstrom. So atoms are about 1 angstrom to 6 angstroms. So this is about 1 angstrom. This would be the hydrogen atom. Actually 1 to 6 angstrom. Larger atoms would be, they could be bigger atoms. 1 to 6 angstroms is also known as 100 picometers to 600 picometers. So people are getting away from angstroms. People are getting away from angstroms because of the decimal point. That's the only reason. So let's say you had an atom that had a diameter of 1.50. Well, the extra decimal point means you have 4 characters. Versus if you called it in picometers, you just call it 150 picometers, which would be 3 characters. And so getting rid of the decimal point is handy thing. And so there's a push switching from angstroms to picometers. And so if we were to use picometers, this would be approximately 100 picometers. Okay, if you look at the nucleus is this small thing in the middle which contains the protons and the neutrons. Now, how are the protons and neutrons arranged? This is some visualization of this. But how the protons and neutrons are arranged is not the realm of chemists. Chemists aren't going to worry about the protons and neutrons because in chemical reactions, let's say when we combust methane, are we transmutating from one element to another? Are we going to be able to make gold from lead? No. Chemists are not interested in this, and so the nucleus doesn't change. Remember, in chemical reactions, the atoms are just rearranged, and so the protons and neutrons stay intact. And so how the protons and neutrons are arranged, that's the realm of particle physicists. They're very interested in how these are arranged. They want to make predictions. For example, I asked you, how do you predict? How do you predict how many types of, let's pick an atom. How many types of platinum atoms are there? And what are they? What's their percentage abundance? Well, we can easily observe that using mass spectrometer, but how would you predict it so that we don't have to do any experiment? Well, that's what the nuclear chemists are working on. The nuclear chemists are looking at this. For us, all we need to know is that there's a tiny nucleus in there. That's it. That contains most of the mass and all the positive charge. Oh, here's this one. If the nucleus is 1 centimeter in diameter, then the electrons would be 100 meters. 100 meters is about 100 yards. So if you have about a football field, it would be about 1 centimeter. Okay, these are the relative sizes. Let's go on. Okay, these are the summary of the results of the, what was the experiment called for the nuclear model? Nuclear atom model?
Gold foil experiment.
What was it? Gold foil? And who was it? Rutherford. So these are the results from the Rutherford gold foil experiments, which we talked about. I'm going to skip this slide. So here are the subatomic particles. The proton carries a unit positive charge found within the nucleus. Okay, this was discovered by Rutherford, but we don't have to talk about that because how did he discover it? Not exactly, because there's other stuff in the nucleus. There's actually more. The discovery of the protons actually credited to a guy named Chadwick, but we're not going to worry about it. Okay, the symbol is P or P plus. The plus is to indicate it's positively charged. So I'm going to start using the P plus rather than the P. Okay, the neutrons are neutral. They don't have a charge, so they're just always N or N0. Actually, Chadwick did this guy.
Do we need to know know those names?
No, you don't need to know the name. Just only one. Which one? Thomson. The reason why only Thomson is because we actually talk about how, you know, what did he use? What was the tool he used or the instrument he used to discover the
Mass spectrometer.
No, actually the mass spectrometer came after Thomson. The mass spectrometer was used. In a way it is the mass spectrometer because that's how the electron mass was determined. The mass of the electron was used using the Thomson tube, cathode ray tube. Yeah, he used the cathode ray tube here. Later on, the development of the mass spectrometer came, but much, much later. The only thing that the cathode ray tube was able to measure was mass of electron. All right, so we know that we have these subatomic particles. We know kind of how they're arranged, right? And we know about isotopes. You know, isotopes are atoms of the same element, but different number of neutrons. They're the same element, so they're going to have the same number, which we call Z, atomic number of protons. Isotopes are atoms of the same element that have different masses. The mass difference comes about from the neutrons. And so we talk about the mass number. The mass number is the number of protons, Z, plus the number of neutrons, N. So this is an exact number. The mass is not exact except for one, and that is carbon-12, based on definition. We talked about this. We talked about the nuclear symbol, you know. And so we have carbon-12 here and carbon-13. You know, both of these are going to have 6 protons, so they're the same element, the carbon. And so they're going to both behave the same. When you eat this carbon, you can't taste the difference between a carbon-13 and carbon-12. They behave the same. When you burn it, they burn the same. Okay, it's just that carbon-13 weighs a little bit more because it has an extra neutron. And so we have to do a little bit of math here, addition and subtraction. If we know we have 6 protons here, how many neutrons do we have? 6. And how many electrons do we have? 6. Okay, over here we're going to have 6 protons, but how many neutrons do we have? 7. Yeah, 6 plus 7 is going to give us 13. And the number of electrons will stay the same. That's 6. All right, so we're going to get some practice doing this now. Barium. Okay. Barium, what is the symbol for barium? This is the elemental symbol, not the nuclear symbol. Barium's symbol is Ba. The atomic number, Z. Well, what element number is barium? Barium, if you go to the periodic table, it's, 56. This is red here on the periodic table. And so the atomic number is 56. The number of protons? 56. Now the number of neutrons, okay, so if we have 56 protons here, this is the nuclear symbol here, so it's a little different. But if we have 56 protons, how many neutrons do we have? It would be 138 minus 56. And so that would be 92? 82 neutrons. So 56 and 82 have to add up to 138. So if that's the case, then the mass number is not a mass. The mass number is the number of protons plus the number of neutrons, which is exactly 138. So this is exactly 138. Now, what is the mass of barium-138? We'd have to put that in the mass spectrometer. And when we put that into mass spectrometer, we get a whole bunch of digits because it doesn't weigh exactly 138. It's very close to 138. And so what is the name of this nuclide? This one is called barium-138. Now, how many others are there? Well, that's not our job. That's the job that the nuclear physicists are looking into. We're just going to look it up in a table. We look it up in a table, we can figure out how many there are and what the percentages are. And so that's just observation, factual observation. How much time do we have? All right, let's do the next one here. If we have oxygen with 10 neutrons, Oxygen with 10 neutrons. Well, let's go with this one because we don't need to know how many neutrons. Elemental symbol? O. Atomic number? So 8. Number 8. Number of protons? 8. So if we have 8 protons and 10 neutrons, then the mass number will be exactly 18, which gives us this. Yeah. We would put an O here, and then O is element 8. This 8 is optional. You don't have to put the O, 8 there, but we have to put this, 18. And so this is a very heavy oxygen. Maybe, in the depth of the ocean, maybe in the depth of the ocean, like at the very bottom, it'd be very interesting to see. But at the very bottom of the ocean, you probably have more heavy water molecules with oxygen 18 versus near the surface. Shallow near the surface, you probably have more oxygen 16. You know what we call that? That's something you can detect. You can detect. Did I talk about ozone? O3? Okay. Probably at the bottom of the ocean, you're going to see enrichment of the heavier oxygen compared to the surface water because of gravity. The same thing can be seen in ozone. You can detect the ozone produced in smog versus the ozone in the ozone layer. The ozone in the ozone layer has a lot more oxygen 16 relative to oxygen 17 and oxygen 18. The ozone on the surface of the Earth has a lot more 17 and 18 because, not more because they're both rare, but just more relative in proportion. So this is a heavier oxygen. And the name of the isotope is oxygen 18. We don't have a special name. We only have a special name for 2. Do you know the special name for the 2 isotopes that I mentioned earlier? Most of them is just like oxygen 18, oxygen 17, but there are 2 that have a special name. Hydrogen 2, which is called deuterium, and hydrogen 3 is called tritium. Yeah, those are the only ones that have special names, but that's just because of historical perspective. Otherwise, they're just like any other isotope. All right, if we have element number 82, what is that? Lead. Lead symbol would be Pb, and it's just LeAd. Number of protons? 82. Number of neutrons? Well, they give us the mass number here. So they're saying it's a 206 mass number, which is the protons and neutrons. So minus the protons, 82. Yeah, 144? Or 124. 124 is correct. And so the nuclear symbol here, this is the way it's usually written. It's written without the Z. And this would just be lead 206. That's what it would be, lead 206. We don't need the Z there because lead we already know is element number 82. Name, it would be just lead hyphen 206. This is zinc 66. Zinc 66, do we have time for that one? Yeah. Actually, what time do we go till today? 25? All right, we're out of time. Actually, so we'll just continue. We'll finish up chapter 5 tomorrow, most likely. But the